In the deep silence between galaxies, gravity writes in fire and shadow. Ancient stars collapse, cities of gravity awaken, and space-time rings with hidden mergers. From first seeds to horizons that admit no return, black holes shape galaxies, stall time, and turn light into whispers. Evidence gathers, anomalies persist, and each answer reveals another edge. The journey into the most terrifying black holes begins. The universe cools and clears after the first light frees itself from matter, a slow lifting of fog that leaves a dark, transparent sea. In that sea, gravity resumes its patient craft. Invisible scaffolding of dark matter gathers ordinary gas, and within those wells the simplest elements drift, compress, and kindle. The first stars appear immense and short-lived, their radiation carving bubbles in the surrounding gloom, their deaths decisive. Some explode and leave nothing behind. Others collapse and leave compact remnants that curve space so strongly that light itself cannot return. In the still young cosmos, these remnants are small, but the stage around them is generous. Gas streams along filaments. Clouds collide. Turbulence folds material inward. The ingredients for a heavier fate begin to assemble. The puzzle begins with speed. Observers find compact bright sources at extreme distances, whose power and spectra reveal matter falling deep into a gravitational well. The distances imply that these engines work when the universe is only a small fraction of its current age, yet their masses approach those in mature galaxies. To become so heavy so soon, they must start larger than expected, or feed with a ferocity that outpaces ordinary limits. This tension opens the search for seeds, the first black holes capable of swift growth. A seed is the quiet origin that later becomes a dominant presence. Its size, place, and feeding habits leave imprints in the light we receive now, so the hunt follows those imprints backward through time. A stellar path begins with unusual births. The earliest star-forming clouds lack heavy elements that help gas cool and fragment, so single stars can grow to extraordinary size. When such a star collapses, a black hole appears already significant. If the surrounding gas remains dense and cool, the remnant can accrete rapidly. Episodes of chaotic inflow, tilted disks, and magnetic turbulence can push accretion above steady limits for short bursts, letting the whole gulp more mass than gentle models allow. In this picture, many small seeds race upward together, and the winners are those who live where the fuel never runs out. A direct collapse path skips the usual bottleneck. In the right neighborhood, a bright companion floods a collapsing halo with ultraviolet light that breaks molecules needed for cooling. Without molecules, the cloud cannot fracture into many stars. It sinks as a whole until gravity takes command, and the fall concentrates matter at the center faster than it can resist. The result is a black hole born already heavy, perhaps 100,000 suns in mass, able to grow into a giant with only modest help. Such births should be rare because the conditions are strict, but rarity is not a barrier when the universe is vast and full of chances. Primordial beginnings are more speculative. During the first instance after the Big Bang, pressure waves and quantum noise could seed brief traps where gravity overwhelms all other forces. Small black holes would evaporate through quantum radiation, but heavier ones could persist. Surveys of microlensing the smoothness of background radiation and the absence of certain distortions pruned most mass ranges, yet narrow windows remain. If any survive within those windows, they could act as early anchors for gas to collect, cutting the queue and jumping straight into the era of rapid growth. Clues arrive from several instruments. The cosmic microwave background fixes the initial ripples that later grow into structure and constrains the energy budget of the first sources. The James Webb Space Telescope reveals compact red galaxies whose light left them when the universe was young, some showing heated gas and concentrated power that hint at accretion. X-ray and gamma-ray observatories measure diffuse backgrounds that must be paid for by many small sources or by a few bright ones. Radio arrays chart neutral hydrogen and seek the faint signature of reionization spreading through the cosmic web. Together, these observations draw boundaries around stories of origin. No single plot may suffice. A mixture might be required. Growth by union deepens the picture. Small halos combine into larger halos and their central objects follow suit. Dense clusters drive heavy remnants toward their cores, where repeated encounters assemble black holes of intermediate mass. When those clusters sink into galactic centers, their cargo adds to the central engine. Mergers heat and stir surrounding gas, sometimes delaying feeding, and sometimes setting the table for the next feast. Gravitational waves carry away energy and momentum during each coalescence, leaving behind a product with a new spin and a small kick that may displace it before it settles again. The result is a path where many modest beginnings converge on a few heavy outcomes. A further boundary is drawn by timing. Stars and black holes pour energetic photons into the cosmic web and change neutral hydrogen back into a thin plasma over several 100 million years. The pace and patchiness of that change limit the number and brightness of accreting black holes in the young universe. Too much hard light too early would leave a signature that is not seen. Current estimates suggest that young galaxies carry most of the load while black holes add a measured share. This leaves room for early engines, but not in numbers that would drown the sky. The constraint does not remove the seeds, it trims their garden. Across these threads runs a quiet theme of urgency. The universe prefers gradual assembly, yet the earliest beacons appear ahead of schedule. Somewhere between diffuse gas and central giants, there is a step that moves faster than expected. It could be a corridor where collapse skips the usual delays. It could be a storm of inflow that for a short while breaks the push of light with the pull of gravity. It could be a merger factory packed into the hearts of tight clusters. The data outline necessities but do not name the mechanism. What they do show is that the first black holes are not merely leftover cores. They are organizers. They shape the flow of matter in their neighborhoods and light the path to the centers of young galaxies. Their presence marks gravity operating at its most decisive, reducing clouds to engines and engines to landmarks that persist for billions of years. The origin of the most terrifying black holes is therefore not a single event but a landscape of beginnings that converge on the same outcome, a deep, well-formed, early, ready to grow. Ancient light records this not as a portrait but as a silhouette thrown across time. The silhouette shows engines already running when the first galaxies learn to build. It shows heat and motion close to a boundary that admits no return. It shows again and again growth that outruns the simple clock. The missing step remains narrow but real, like a hidden passage through a cliff. The next layers of evidence will either widen that passage or close it. But for now, the map of the earliest universe keeps a blank, where the seed should be a quiet space reserved for an origin that moves faster than expectation and leaves behind a shadow that still rules the centers of galaxies. Across the early universe, before galaxies have settled into familiar disks and spirals, silent giants already sit at the centers of young assemblages of stars and gas, shaping the growth around them as if they have been given a head start. Their signatures travel to us as quasar light, a fierce blend of ultraviolet and X-ray and radio power, made by matter spiraling inward. Spectra reveal broad lines from gas moving at a fraction of light speed, and the shapes of those lines allow estimates of mass that reach billions of suns when the universe is only a few 100 million years old. telescopes that search wide and deep from the Sloan Digital Sky Survey to the Panoramic Survey Telescope and Rapid Response System have mapped these beacons and follow up with space observatories and giant mirrors on mountaintops, shows that the hosts of these engines are still young and busy. The James Webb Space Telescope peers into red wavelengths where early dust and gas glow and finds compact galaxies with turbulent star-forming regions, thick with cold clouds and threaded by bars and bridges left by recent mergers. The Atacama Large Millimeter Array detects carbon monoxide in broad wings that suggest powerful outflows and faint dust that already blankets central lanes, forcing the conclusion that massive stars lived and died quickly to enrich this gas. Everything looks fresh and unsettled, yet in the heart of these systems, a black hole has already become a dominant presence. The pace of that ascent sets the mystery. If a black hole grows by swallowing gas at a steady rate, defined by the balance of gravity and the outward push of light, then reaching 1 billion solar masses within so short a time, requires either a very heavy birth, an almost continuous supply of fuel, or repeated episodes of growth that exceed the gentle limit. Observations point to a patchwork of these routes. In some early hosts, the central engine is surrounded by warm, dense gas that can fall inward faster than starlight pushes it away. In others, the chaotic geometry of inflowing streams may break the push of radiation by bending and shielding, letting pockets of matter fall as if the lighthouse were partially veiled. Magnetic fields near the disk can also channel energy into jets that carry away heat, and angular momentum turning a choked inflow into a more efficient funnel. Any such tricks, even if brief, could stack over time to move the mass up the ladder faster than standard models predict. The size of the host galaxy complicates the story in another way. In the mature universe, black hole mass tracks with the central stellar velocity dispersion and with the bulk of the galactic bulge as if a feedback conversation links the ether and the city it inhabits. Early giants sometimes appear to sit above that relation heavier than their hosts would suggest. The James Webb Space Telescope resolves clumpy disks and protobulges, whose stars are only beginning to assemble, while the spectra imply central masses that already occupy a large fraction of the eventual budget. This mismatch need not be permanent because galaxies can catch up through mergers and steady star formation, yet at early times the central engine often looks overbuilt. Where the relation comes from is itself part of the puzzle. Outflows launched near the event horizon travel far into the host heating and stirring gas, suppressing star formation in some places and triggering it in others by compressing clouds. These feedback loops can establish a balance in which the black hole grows until its energy output expels or heats the remaining fuel, leaving behind a galactic core tuned to the engine. In the first billion years, however, the loops may not have had time to close. We may be catching systems mid-sentence with the black hole speaking loudly, while the galaxy has not yet answered. Gravitational wave astronomy hints at another accelerant. The early universe is rich in small halos that merge often, and their central seeds should merge as well. Each coalescence releases a burst of space-time ripples and produces a remnant that can swallow fresh gas with a newly aligned spin. Repeated mergers can step the mass upward in sudden increments. The laser interferometer space antenna, when it flies, should hear these events from high redshift, but even now models tuned to current detections by ground-based observatories suggest a sea of early unions that could tilt the odds toward heavy central objects before galaxies mature. Meanwhile, the environment continues to feed the giants. Cold streams from the cosmic web can dive into halos without heating, delivering gas straight to the center. Dwarf galaxies fall in and donate their own central seeds along with reservoirs of gas and stars. Tidal interactions scrape angular momentum from inflows letting clouds sink, where many processes conspire to remove spin matter, falls, and where matter falls, energy is released in light and wind and jet that can be seen across the sky. The balance of inflow and feedback is delicate, but in the first scenes it seems to favour inflow long enough to build the giant cores we now observe. This does not mean that every early halo breeds a monster. Many environments are poor in fuel, or stabilise into disks where star formation consumes gas before it can fall inward. Some central objects may be kicked by gravitational wave recoil and wander for a while, starving until they resettle. Yet the record of distant quasars proves that in a non-trivial fraction of cases the circumstances align, so that a central black hole grows to supermassive scale ahead of its city. The universe then wears a necklace of beacons that light up ionization and leave fossil imprints in the statistics of background radiation. The silent giants awaken, and their awakening sets the rhythm for the layers around them. The bigger they become, the more they sculpt the weather of their hosts. They carve cavities in hot gas and draw filamentary inflows. They align magnetic fields on scales of tens of thousands of light years. They imprint rotation and precession on jets that can drift over millions of years like slow pencils sketching in the dark. When their fuel runs low, they fade to a low hum that still regulates the temperature of the local medium. When fresh fuel arrives, they brighten again as if the switch had always been waiting. This elasticity resembles memory. The central engine remembers earlier episodes through its spin, through the orientation of its magnetic field, through the carved channels that make it easier for new gas to find the throat. That memory helps explain why growth can remain fast even when the outer scene is chaotic. It also deepens the unease because it means that once a path to rapid growth is opened, it can reopen. The timelines fray because the system does not start from scratch each time. It moves forward with a record written in the shape of space near the horizon. The result is a population of central black holes that appear too grown for their age, and a set of host galaxies that learn and adapt around them. The giants are not loud in their own frame. They are patient wells that alter motion by their presence. It is the matter that screams on the way in. Light and wind carry the evidence outward, and across cosmic time that evidence reaches us still puzzling, still ahead of schedule. The question then sharpens. If these giants can awaken so early, what subtle doorway did they find through the constraints of cooling, angular momentum, radiation pressure, and limited time? Since that doorway is narrow, the universe must have guided many streams through it with surprising efficiency. The next sections will follow that guidance into the places where gravity rules most tightly, to see whether the same urgency appears there, and whether the giants show any signs of the missing step that lifted them before their cities could catch up. Within mature galaxies, the core resembles a city whose avenues are gravitational, where every street bends toward a central well, and every landmark is carved from motion. Stars hurry along layered highways, some in near-circular lanes that keep their distance, others in elongated loops that dive inward before sweeping back into the bright bulge. Gas drifts more slowly, colliding and cooling, shaping rings where orbital rhythms lock in step, and bars where torques trade angular momentum between the inner lanes and the outer disk. Dark matter sets the grade beneath all of this, a quiet scaffold that fixes the depth of the common well, while the luminous traffic reveals its contours. The central black hole does not rule by devouring because most matter misses the narrow throat. It rules by editing the options, pruning orbits, setting precession, and writing a subtle grammar into the possible paths that stars and gas can take. Telescopes trained on nearby galaxies read this grammar in starlight and in the glow of shocked gas. In the Milky Way, individual stars close to the center are tracked for years as they curve around the compact object Sagittarius A star. their periapsis passages flashing past the point of closest approach at speeds that turn years into minutes. Each track is a line drawn on the local map of space-time, and together those lines reveal a mass dense enough to fit inside a region, smaller than the orbit of Mercury, a quiet engine that whispers in near-infrared flares and low radio hum. In the giant elliptical galaxy, known for a shadow imaged by the Event Horizon Telescope, the surrounding stars are less distinct, but the pattern of their velocities and the way gas rotates show a similarly dominant presence. These portraits anchor the idea that central black holes inhabit most, perhaps nearly all large galaxies. Patterns in these cities of gravity look orderly at first glance. The average motion of stars relates to the mass of the central engine, as if a hidden negotiation sets a compromise between the crowd and the well. Bulges with fast random motions host heavier black holes, and delicate disks with slow centers tend to harbour lighter ones. Pairs of numbers fall along a relation that appears simple enough to serve as a rule. Yet the closer the view, the more the rule bends. Dwarf galaxies sometimes carry outsized black holes that sit above the trend. Starbursting nuclei can mask a central engine on the small end, pushing it below the line until the storms settle. Mergers shift points upward in sudden steps. Outflows inflate bubbles that add heat to the local gas, and stall star formation subtly changing the very measure used to compare. Order holds in the mean, but the individual neighbourhoods argue. Gas complicates the balance further. High-resolution millimetre arrays trace cold molecular lanes that wrap the centre like braided rivers. In some galaxies, those lanes stall into rings that feed stars instead of the engine, a defensive moat that keeps gas at a safe remove. In others, the lanes show abrupt kinks where a bar channels material inward, past resonant barriers that usually trap it. In still others, warped disks cross like slipped pages in a book, and the gas from one page shocks into the gas on the other, losing angular momentum and sliding inward through a gap that opens only briefly. Where the gas can settle into a thin coherent disk close to the centre, spikes in emission lines betray the presence of water mazes that mark precise orbits. Those clocks allow a direct weighing of the central mass and show a plane tipped relative to the outer galaxy, a mismatch that carries memory of how the last supplies arrived. Even when orbits look steady, instabilities lie in wait. A faint bar can grow from noise and then dissolve, leaving behind a ring that feeds bursts of star formation. A small satellite galaxy can swing by and stir the nucleus driving gas inward on lopsided paths. A nuclear star cluster, brilliant and compact, can compete with the black hole for control over nearby stars, changing who holds the leash over which orbits. In triaxial bulges, where no axis is privileged, families of box orbits wander close to the centre and can be scattered by even a modest central mass, a quiet mechanism that reshapes the inner density profile. What looks like balance is often cycling between states with a grace that conceals strain. Jets extend the influence of the core far beyond the starry streets. They rise from near the event horizon, where tangled magnetic fields grip the disk and fling out collimated beams at near light speed. In the largest galaxies at the centres of clusters, those jets carve cavities in the hot intracluster gas, leaving paired bubbles that rise like slow balloons and deposit heat into the atmosphere. The bubbles prevent catastrophic cooling that would otherwise rain gas onto the core and overwhelm it with fuel. The engine therefore writes weather far from home, and that weather feeds back to regulate the engine a loop, whose apparent poise hides many pathways to failure. Sometimes the regulation works too well, and the core starves. Sometimes it fails, and the core brightens into a quasar that sweeps its own city clean. Stars near the centre trace other secrets. A few travel on orbits so tight that relativistic effects change their timing and orientation in ways that ordinary gravity cannot explain. Light from those stars reddens and lags as they dive and climb. The pericenters rotate slowly, turning each return into a shifted rendezvous. In extreme cases, a star can cross the unseen boundary, where tides become knives, and its body stretches into a stream that wraps the black hole in glowing threads. The flare from that disruption illuminates the immediate architecture, revealing a disk thickened by heat, a wind that rises from the inner edge, and a cap of high-energy light where shocks meet. Every such event is both a tragedy for the star and a test for the map, and the map gains marks that do not fade quickly. Beyond the stars and the cold lanes warm, ionized gas fills cavities and threads, cones that point along the spin axis of the central engine. Narrow lines from heavy elements trace outflows that accelerate, and then coast slowed only when they encounter denser clouds. In some galaxies, those cones align with dust lanes and indicate a long-lived jet that has carried momentum for millions of years. In others, the cones are misaligned from the current jet, suggesting that the spin axis has reoriented perhaps after a merger, or after the engine swallowed a thick disk with a contrary tilt. The core therefore keeps a layered history in its geometry, a palimpsest written in light and motion. All of these features together produce the impression of order. The average relations between central mass and stellar motions, the common morphologies of rings and bars, and the similar ways that jets carve bubbles all suggest a shared playbook. Yet the anomalies are not footnotes. They are the edge cases that carry the next instructions. Rings that refuse to feed the core for far longer than models expect. Black holes that sit sideways relative to their hosts. Nuclear clusters that appear too massive for the ambient density and bulges that host engines 100 times heavier than their measured dispersion would predict all imply that the rules are conditional. The city is stable only because instability is penned into every level of the design. A galaxy can remain quiet for a very long time and still be only one small shove away from a new state. A passing companion, a change in the outer supply of gas, or the angular momentum from a single infalling cloud can open the narrow lane that leads to the throat, and once open, the lane can stay open through the structures it creates. The central black hole then writes its presence into the city with a fresh round of edits, and the streets bend a little more toward the well. The result is a living equilibrium convincing from afar, twitching underneath. It is this quality that makes the cores feel terrifying in a slow way. Nothing visible needs to break for everything to change. The city holds together, the lights remain on, and yet below the brightness the rules shift by a degree that will matter over millions of years. The next discoveries will focus on those degrees, tiny drifts in precession, subtle tilts in disks and slight delays in flares, that together may reveal how the order keeps its balance by almost falling. Across the long arms of Earth, laser beams bounce between mirrors suspended in deep vacuum tunnels, and in their interference pattern, a new astronomy is born. The laser interferometer. Gravitational wave observatory listens in one country. The Virgo interferometer listens in another, and the Kamioka gravitational wave detector in Japan joins as a third ear. Together they feel the faint stretch and squeeze of space-time as compact objects rush together and collide. The first clear signal arrives as a rising tone that swells and cuts off the fingerprint of two heavy black holes, spiraling inward, merging and settling into one. Since then, the catalogue grows through observing runs separated by seasons of upgrades. Each detection writes a short story in 3 acts, an in spiral that reveals masses and spins a violent union, that flashes peak power, and a ring down that hums as the remnant relaxes. From these acts, patterns emerge that redraw expectations. Many binaries are heavy, much heavier than the black holes known from X-ray binaries in the Milky Way, and their spins often lie misaligned with the orbit as if their lives before pairing were separate and chaotic. Some coalescences hint at eccentric paths that only circularize later clue that dense clusters or repeated encounters may be the matchmakers. A few mergers point to members that likely came from an earlier union stair-steps in mass that build hierarchical families. One result carves a number where theory had drawn a blank stripe, a black hole heavier than the limit expected, from ordinary stellar death inside the gap shaped by pair instability, suggesting either uncommon stellar evolution or prior mergers. Signals from black hole and neutron star pairs add a further layer carrying an outline of tidal tearing that maps the stiffness of atomic matter at densities that no laboratory can attain. Against this ordered success, small leftovers linger after careful subtraction. Analyses that stack many events to search for faint echoes in the ringdown find hints that do not reach certainty and yet refuse to vanish. Residual power appears at delays that would match reflections from a surface just outside a horizon, the sort proposed in models where quantum effects roughen or delay the boundary. Instrumental noise can impersonate such features, and teams build catalogues of glitches and train algorithms to disregard them. But the suspicion persists because the residue respects gravitational timing more than hardware habit. Whether these are true echoes or a statistical wish remains unsettled, and that uncertainty is itself a clue worth preserving. Independent puzzles wait in the distribution of spins. If massive stars in tight pairs collapse without much disturbance, their spins and the orbit should align. In the data, many spins tilt and some tilt backward, a quiet vote for dynamical formation in clusters where exchanges are common. Yet a subset shows near alignment as if two channels run in parallel, and the universe refuses to pick only one. Most heavy black hole mergers remain dark as expected if they happen in clean environments with little gas, but a handful of candidates appear near flares from active galaxies, and one case shows a brightening consistent with a kicked remnant ploughing through a disk. As the networks grow more sensitive, the horizon for detections moves deeper and widens toward lighter masses. Upcoming runs will add a new instrument in India, and further improvements in Europe and the space-based laser interferometer. Space Antenna will later open the band where supermassive black holes slowly pirouette. At still lower tones, teams that time the regular radio pulses of millisecond stars combine long records to reveal a background of very low-frequency waves, likely made by many pairs of supermassive black holes wandering toward union. Together, ground-based interferometers pulsar timing arrays, and the future space mission will stitch a spectrum from the deep bass of galactic giants to the bright treble of stellar remnants. The formation channels are varied. In dense star clusters, three-body encounters swap partners and create tight eccentric pairs that meet quickly. In gas-rich disks around active galactic nuclei drag and migration shepherd pairs together. In dwarf galaxies with shallow wells, kicks from earlier mergers can eject remnants and seed the field. Each channel leaves marks in mass and spin, and the catalogues already begin to sort them. Every time a boundary seems firm, a detection presses against it. Clean signals, once thought to be simple, carry a stubborn residue of structure that whispers of nearby complexity. Even the ringdown, hailed as a pristine tone from a classical horizon, may include subtle overtones that endure longer than simple models predict. If overtones can be confirmed in many events, they would act as a spectroscopy of black holes, testing the relation between mass spin and frequency, without opening the interior and yet demanding that the interior be consistent. The promise is precise: two or more tones can overconstrain the identity of the remnant, and if they disagree, the disagreement cannot be pushed onto the environment because the environment is quiet during the ringdown. Such a test is as close as one can come to knocking on the boundary and listening for hollow notes. The most unsettling possibility is also the most disciplined. Perhaps the residues are not artifacts and not accidents, but the first low notes of new physics horizons that are not perfectly absorbing hair, that carries a faint memory of what fell, or quantum interference that changes the phase of the outgoing waves by a breath. Such ideas must pass a narrow gate because they touch the cleanest predictions of general relativity, and yet the gate is open, however slightly, because the instruments are now precise enough to make the attempt. When the interferometers began listening, the goal was simply to hear. Now the goal is to hear more than expected. In every run, the catalogue lengthens and the maps of mass and spin space fill with points that refuse to sit exactly where they were told. The echoes may prove to be nothing but carefully modelled noise. The tilts may dissolve into a tidier story once the numbers are large, and the overtones may match the textbook when measured better. Or they may remain. If they remain, the cities of gravity will gain a soundtrack with stray notes that compel a change of plot, and the terrifying part will be simple. The universe may already be telling that story in gravity, and we are only now learning enough musical theory to notice the counterpoint. The Event Horizon Telescope gathers a planet-sized eye by linking radio dishes from dry mountaintops, high plateaus, and the polar ice turning Earth into a temporary mirror that resolves structures near the brink. In coordinated nights of clear weather, antennas in the Atacama, in Hawaii, in Arizona, in Mexico, in Spain, and at the South Pole listen together at a wavelength chosen to slip through interstellar fog. Atomic clocks at each site keep time so strict that the separate recordings can later be braided into a single vision, and when that braid tightens, the image plane fills with a slow whirl of light near a dark center that behaves like a silhouette against fire. In the giant elliptical galaxy called Messier 87, the first portrait shows a ring with an uneven crescent brighter on one side where plasma rushes toward the observer and light is beamed and bent. The darkness at the center is not a true hole but a bowl carved by gravity, where photons that would have escaped are captured or thrown into loops. The presence of a ring and the size of the bowl match predictions that depend only on mass and spin, and on how space-time focuses light near the last safe orbit. The image becomes a standard not because it is perfect, but because it is constrained a pattern that many different models must reproduce to be acceptable. The constraints grow stronger when polarization is mapped. Polarization is the fingerprint of magnetic order in the glowing gas. When the polarized light is resolved around the ring, a set of line appears like grain in brushed metal, wrapping and twisting in a way that reveals fields strong enough to corral hot matter into a thick, magnetically arrested flow. Those fields promote the launch of jets and regulate how heat and angular momentum move through the disk. In the Messier 87 image, the polarization vectors spiral around the shadow, a sign that gravity and magnetism are locked together in the final stretch before the horizon. The black silhouette is therefore not empty. It is an active edge where fields and particles and curved light converse. The second portrait of Sagittarius, a star at the centre of the Milky Way, arrives with different challenges. The radio waves cross our crowded neighbourhood and scatter on irregularities in the interstellar plasma, blurring and dancing in a way that must be removed with careful modelling before the true structure can appear. The source itself changes on timescales shorter than a night, because the orbital period so close to the centre is only minutes, and the telescopes can integrate only snapshots while the pattern shifts. Yet when teams combine many reconstructions and check them against the raw interference data, a similar ring appears with a dark middle and a bright crescent, whose orientation changes from night to night as the flow flickers. Polarization again reveals an ordered magnetic field close to the boundary, and the overall size of the silhouette points to a mass that matches independent measurements from the orbits of nearby stars. Two portraits that differ in mass by billions of suns still rhyme at the edge. This repetition is both comforting and unsettling. It comforts because it vindicates the geometry of general relativity and the basic structure of an optically thin hot accretion flow. It unsettles because small differences carry great meaning. In simulated flows that include gravity radiation and magnetized turbulence, the thickness of the ring, the ratio of the bright crescent to the dimmer side, and the degree of polarization depend sensitively on how gas falls, on how much it cools, and on the direction and magnitude of the spin. The Event Horizon Telescope cannot yet resolve the thin photon ring that theory forecasts as a stack of increasingly narrow-lensed loops, but it can sense its presence as a bias in the measured size and as a preference for certain closure phases in the interference pattern. Even a whisper of non-circularity, a slight flattening or tilt, would point to deviations in the spin geometry, to a disturbance in the flow, or to a scattering correction that is not fully removed. Teams place limits on departures from circular symmetry that are small enough to matter the silhouette shifts by a whisper, and that whisper is what the next generation will try to hear. Magnetic order deepens the mystery. Polarized maps show fields threading the inner flow and twisting in patterns that imply a build-up of magnetic pressure near the inner edge. When pressure becomes strong enough to impede inflow, the disk enters a magnetically arrested state, in which clumps and tongues of gas break free in fits. This regime favors the formation of jets because rotating fields tap the spin of the black hole and fling energy outward along the axis. In Messier 87, a jet stretches far beyond the core, and the alignment between the polarization at the ring and the orientation of that larger scale beam suggests a continuous engine from horizon to halo. The same alignment is less clear in Sagittarius A star, where the flow is weaker and no long jet is seen, yet the polarization still testifies to near-horizon structure that chooses an axis. The danger in such order is that it might be too explanatory. If the fields are strong and the gas is hot, one can account for the crescent and the ring, and even for the variability with a single family of models. But then the light curves show flares that drift like small embers around the ring, as if a compact knot orbits, and then dissolves, and the timing sometimes implies speeds and positions that lean toward or against particular spins. The polarization angle can swing in a way that indicates a loop of field wrapping and snapping. The changes are subtle, yet they repeat with enough consistency to force questions about the stability of the inner flow. Whether the brightness clumps are regions of reconnection, or faces of a thicker structure whipping through view, or temporary funnels in a churning atmosphere remains open. The Event Horizon Telescope extends its resolving power not only by adding dishes, but by expanding frequency coverage, by improving coherence time, and by learning to watch longer without blinking. Each improvement turns a static portrait into a slow movie. In a movie, the silhouette should hold steady while the fire around it swirls. If the silhouette shifts more than expected, that shift cannot easily be blamed on foreground distortions or on instabilities far from the center. It would imply either a change in the mass distribution inside the last orbits, which is not allowed by known physics on such short intervals, or a delay effect from a boundary that is not perfectly absorbing. The latter idea enters the room quietly, because it occupies the narrow space where classical and quantum descriptions meet. A surface just outside the horizon roughened by quantum structure could act like a weak mirror for certain modes, adding a faint delayed echo or a tiny wobble to the ring. The data do not demand such a thing, but they leave a sliver of space where it could hide, and the combination of images, light curves and polarized patterns is beginning to corner the possibilities. The silhouettes also speak through their size. The apparent diameter depends on distance and mass in a predictable way, and so the measured rings can be used as rulers. In Messier 87, the inferred mass agrees with stellar dynamics, and in Sagittarius A star it agrees with the stellar orbits measured over decades. This concordance is not trivial. It says that the light path near the brink behaves as forecast, and that the bowl carved by gravity has the depth and width one expects for a black hole of the measured mass. Deviations would have signalled either a different compact object or a change in the bending of light, and none is seen at the present precision. Yet the pressure to go beyond is high, because the most interesting possibilities live just below the current resolution. A thinner photon ring layered with subrings, a persistent asymmetry that tracks with spin over many cycles, a stable offset between the geometric centre of the ring and the jet base, a slight lag between polarization angle and flux that hints at reconnection at a preferred radius. Each would open a door. Plans already exist to place radio antennas in space to lengthen the baselines, to add more sites on Earth to fill gaps in the coverage, and to observe at higher frequencies where scattering weakens and finer details stand out. The intention is not to redraw the silhouette, but to listen for the whisper of its shift to separate the ring from the turbulent fire, and to weigh the role of magnetic order in setting the scene. In that effort, images stop being trophies and start being instruments, and the terrifying part becomes quiet again. A boundary that accepts everything, without reply, could still leave a trace in the geometry of the light that escapes, and that trace, however faint, would be a message from a place that admits no messages. Space telescopes that see an X-ray light turn the darkness near black holes into a canvas of lines and edges, and by those marks the inner flow can be sketched. The Chandra X-ray Observatory and the X-ray Multi-Mirror Mission. Newton watch with sharp sight and broad grasp, separating colours of high-energy light and following how that light rises and falls. Their spectra carry a familiar fingerprint, a bright iron line near 6 to 7 kilo-electron volts, and a hard tail that extends to tens of kilo-electron volts, both resting on a softer glow from the wider disk. The iron line is not narrow as it would be in a calm lamp. It is smeared and skewed with a long red wing that slides to lower energies, a mark of photons that climb out from deep in the gravity well and lose energy on the way. The shape depends on the spin of the black hole and on how close the bright inner gas orbits. A fast spin squeezes the innermost stable circular path inward, letting iron atoms closer to the brink imprint deeper red tails. By fitting these shapes with careful models, teams can weigh spin in binary systems and inactive galactic nuclei, and the answers vary from slow to near maximal rotation. Yet the fits rarely feel final. The line sits on a reflected continuum from hard light bouncing off a dense surface, and that glow itself bends and changes as geometry shifts. High-energy photons likely come from a compact corona, a swarm of hot electrons just above the disk that scatter softer light into a harder spectrum. If the corona moves closer to the horizon, gravity bends more rays back into the disk, brightening the reflection, deepening the iron features and dimming the direct view. Observers sometimes see precisely that pattern as the source hardens and the reflection strengthens. The total flux falls as if the lamp had sunk closer to the pit. Timing adds a second ruler. Short flares in the hard continuum echo a few heartbeats later in the reflection, and the delay maps the light travel time between the corona and the inner disk. In some galaxies, the soft echo lags the hard drive by only a few tens of seconds, even though the central mass is millions of suns, implying that the lamp sits only a few gravitational radii above the surface. In stellar mass systems, the lags shrink to milliseconds, a near mirror of the same structure scaled down by mass. This reverberation confirms that the bright iron line does not come from far away. It is written close to the edge where time slows and orbits race. That closeness should fix the tune, yet the tune drifts. In several sources, the iron line shape changes on hours to days, and the continuum swings with it as if the corona were breathing, growing taller, and then flattening to a more compact base. A lamp that alters its height by only a few gravitational radii can produce such shifts, but the steps look abrupt and sometimes correlate with radio flares, suggesting that the corona and the jet base share identity for a time before part of the structure is torn free and shot outward. Soft lags also stack into more complex delays at higher energies that imply scattering in a stratified atmosphere, so that the corona may be less a single blob and more a layered fog. The hunger of the inner flow appears in flares that rise toward the iron band like sparks carried by wind. Chandra has watched low-level activity near the centre of the Milky Way, where short X-ray flares light the region around the quiet giant. The shapes of the flares hint at magnetic reconnection in the inner flow, a sudden rearrangement of fields that heats electrons and turns the corona briefly fierce. In brighter active nuclei, giant outbursts reshape the reflection pattern for days, which can be read as a flash that travels across the disk lighting annually, in order a wave that moves almost at light speed along the surface. Such events argue for a corona that is patchy with hot spots that flare and fade like coals in a fast wind. The familiar fingerprints smudge at the edges in several further ways. Some disks show very strong winds that carry signatures of heavy elements at thousands of kilometers per second, with absorption lines that slide in step with the continuum, suggesting a funnel of gas that accelerates close to the source and then thins. In extreme cases, blue shifted features imply speeds of a few tenths of the speed of light, an ultra-fast outflow that could help clear the nucleus and regulate the supply of fuel. These winds complicate the iron line because they absorb and re-emit and sometimes add their own broadened features. Distinguishing a reflection wing from a wind trough becomes careful art, and small errors in one part of the model can masquerade as false spin or false height. In a few well-studied binaries, quasi-periodic oscillations ripple through the light curve and appear stronger in the hard band than in the soft band, a rhythm that many models assign to precession of the inner flow under the combined influence of spin and frame dragging. If the precession picture is correct, the iron line should wobble with the same rhythm as different azimuths rotate into view. Observers have chased this with phase resolve spectroscopy, and in some cases find the expected swing, but in others the beat drifts or breaks into harmonics as if more than one structure is turning, or as if the disk thickens and damps the sway. Even when a simple precession is seen, the required scale height and tilt can be difficult to reconcile with other constraints, leaving behind the sense that the inner flow is poised at the edge of multiple instabilities and climbs from one to another during an observation. Another smudged edge comes from light that should be steady but is not. Reflection from the disk ought to vary more slowly than the illuminating continuum if the disk is large and smooth. Yet there are cases where the reflected component jumps as if a small area close to the black hole brightened strongly, while the rest stayed calm. A corona shaped like a narrow spine could do this lighting only an inner annulus, while the outer disk sees little change. That idea matches some high-frequency lags that are too short for a wide lamp. It also matches polarization hints from other bands that prefer a small aligned source. Still other events call for a compact blob that moves laterally at relativistic speed around the axis, making a carousel of bright spots that we see in turn as the blob passes by the line of sight, consistent with orbiting knots seen at millimeter wavelengths in the galactic center. The hunger shows teeth most sharply in the iron line at the lowest energies where the red wing reaches. That wing marks photons born deep in the potential well, and the exact cutoff tells whether the disk reaches the innermost stable circular orbit or truncates farther out. In low states of some binaries, the wing shortens and the continuum hardens as if the disk pulled back and a hot inner flow took over. In high states, the wing lengthens again as the disk refills the center, yet even this tidy story bends. Some low states show long wings that argue for a disk that never left, while some high states show short wings that look like a retreat. Perhaps the state change is not a simple radial move, but a change in surface density and thickness that leaves the inner radius near fixed, while altering how well the surface reflects. Or perhaps a puffed inner flow replaces a thin disk without moving the effective boundary, changing only the angle between the lamp and the mirror. The line sees geometry, not labels, and the geometry may skip across categories. Through all of this, the instruments build maps in energy and time, and those maps insist that the last stable orbits are both rigid and volatile. They sit where gravity says they must, and yet the brightness that washes over them behaves like weather. The terrifying aspect arrives from this mixture of constraint and surprise. The iron fingerprint remains recognizable, anchoring mass and spin, and placing the mirror close to the brink. The hard tail and the soft echoes agree with a compact lamp that hovers only a few gravitational radii above that mirror, but the details do not sit still. Winds rewrite the edges. Hot spots walk the ring. The lamp rises and sinks by a small height that nonetheless rearranges pathways of light. When the familiar marks blur, they do not vanish. They expose structure just below the current ability to separate layers. The next instruments will push into higher energies and faster timing to peel those layers apart. Until then, the smudges are not flaws. They are the handwriting of a place where gravity writes quickly and the ink does not have time to dry. Jets rise from the smallest neighborhood near the event horizon and stitch the largest rooms of the universe together narrow beams that keep their shape for hundreds of thousands of light years and sometimes for millions. They begin where magnetic fields coil around hot plasma in the inner flow and thread the spinning black hole so rotation and gravity can be tapped and sent outward. Lines of magnetic force twist, store energy and unwind. The unwinding launches matter and light along the axis at speeds that approach the speed of light. Very long baseline radio maps show strings of bright knots that move outward and sometimes seem to outrun light, an illusion from geometry and timing, when a pattern races almost as fast as the photons that carry its image. The knots mark shocks where faster flow catches slower flow, and where magnetic reconnection heats particles that then radiate across radio-optical and high-energy bands. In nearby giants such as the galaxy in Virgo with a shadow imaged by the planet-sized radio array, the jet carves a channel and then swells into lobes that rise like paired balloons. The lobes push hot plasma aside and leave cavities whose rims glow in X-ray light ripples and arcs that are fossil waves of repeated outbursts. Those waves carry enough energy to keep the central atmosphere warm, stopping a runaway cooling that would otherwise dump gas onto the core. Thus, a thin beam controls a thick halo, closing a loop between a horizon measured in minutes and a cluster that stretches for millions of light years. In other hosts, the jet is shorter and meets dense clouds within the galaxy, where it bends and breaks and light star formation in compressed filaments along its path, only to bleach its own work when the flood of radiation catches up. Magnetic fields guide the flow like rails, and pressure from the ambient gas helps collimate the beam as it drills a channel. Inside the beam, the fields wrap in a helix that damps small disturbances, but can plant waves that grow into knots and wiggles. Radio and optical telescopes follow these knots. High-energy observatories catch them flaring in gamma rays when shocks compress the field and re-energize particles. Timing across bands yields sizes and speeds. Where the beam meets dense clouds, pieces of the foreground are sandblasted and carried along, and that entrainment slows the flow and fattens the beam. In the largest central galaxies of clusters, broad plumes feed bubbles that grow and detach, and the period of this breathing can be read from ripples in the X-ray atmosphere sound waves on scales of tens of thousands of light years. Straight lines also bend with intent because the source can pivot. If a black hole swallows a thick disk with a different tilt, the spin axis can precess, and a swiveling engine draws a gentle spiral in the sky. Some radio galaxies show crossed wings that may record a past alignment and a present one, or the trace of a binary black hole that torqued the inner disk. Jets also carry messengers that are not light. Shocks and reconnection near the base can fling protons and heavier nuclei to extraordinary energies. When those particles strike gas, they create pions that decay into gamma rays and neutrinos. A high-energy neutrino recorded by the IceCube Neutrino Observatory coincided with a flare from a distant jet, a tentative link between a black hole engine and one of the hardest messengers to produce. Polarization maps reveal ordered fields that run along the beam and rotate with distance as expected if the flow carries helical field from the launch zone. The sense of rotation and the degree of order change during flares, suggesting that the field loads and unloads energy like a spring. On the finer scales, very long baseline interferometry resolves bases that start wide and then squeeze as if a magnetic nozzle tightens, and then releases only light days from the horizon. Stationary features near that nozzle act like recollimation shocks that briefly narrow and brighten the beam before it relaxes again, and far downstream, a terminal shock inflates the lobes and closes the circuit. A galaxy that once carried a strong beam may show cavities in its hot halo for tens of millions of years after the core has dimmed. The cavities rise and expand and lift enriched gas from the center, mixing heavy elements into the broader medium and changing how quickly new stars can form later. Despite this broad picture, puzzles remain. Some jets fade quickly in welcoming environments, others keep collimation through turns that should shred a fast flow, and strings of compact knots can appear with gaps between them, as if the engine starts and stops. Opposing jets in one host can differ in brightness. More than orientation can explain hinting at asymmetric launch or hidden obstacles. Even without a lens, a jet may trace a slow, repeating curve, the print of either a wobble in the engine or a wind in the medium. This speculative doorway opens at the base. If the power of a jet truly comes from black hole spin tapped by magnetic fields, then the jet is a lever that converts rotation into ordered energy. The efficiency of that lever depends on how much magnetic flux the inner flow can hoard. A magnetically arrested state collects more flux than a quiet state, and the resulting jet is stronger and more stable, a picture that matches polarized rings near nearby horizons and the alignment of inner fields with large-scale beams. Yet the path of flux into the engine is unclear, and the reason it sometimes leaks away is unknown. Perhaps a long train of gas with the same magnetic polarity is needed to build the strongest nozzle, and a change in polarity weakens the beam and lets the inner flow reset. Perhaps the space just outside the horizon is not perfectly smooth, and tiny quantum corrugations reflect a trace of energy back into the flow and alter the launch in a way that shows up only as a small change in the width of the ring or in the timing of a flare. In the end, jets remain the most direct handwriting of black holes on intergalactic scales, drawing lines that last longer than the stars that see them. They are narrow enough to suggest control, and wild enough to carry storms, the straight lines that bend with intent. Between the stellar remnants that weigh a few tens of suns and the central monsters that weigh millions to billions, there should exist a middle class that bridges the scale, yet the middle class hides. Astronomers name them intermediate mass black holes and build a case from hints that appear in very different rooms of the universe. In dense clusters of old stars, the motions near the core sometimes swell above what the visible mass can hold, as if an unseen anchor sits in the center and tugs a little too hard. Space telescopes watch the proper motion of thousands of stars over many years and derive a velocity profile that rises toward a cusp. Ground-based spectroscopy of integrated light adds another measure. This signal is small and easily confused by a cluster of dark remnants or by orbits that are not evenly distributed. Yet in a handful of systems, the simplest fit prefers a central black hole of a few thousands of suns. A similar whisper comes from star clusters in nearby galaxies, where the combined starlight can be weighed against the speed of the inner core. None of these claims stand alone like a portrait. They ask to be understood as part of a pattern that repeats enough to become persuasive. Other clues arrive as pointed lights that are brighter in X-rays than most stellar engines can sustain. These ultraluminous sources blaze from the outskirts of galaxies and from small satellites, sometimes flickering with a period that evokes an orbit, sometimes showing a soft cool disk and a luminous hard tail, as if the accretor were heavy and the inner temperature therefore lower. In several cases, radio and optical counterparts reveal a small cluster or a stripped nucleus nearby, a plausible cradle for a middle black hole that feeds on a captured companion or on gas shed by aging stars. Skeptics note that a stellar mass black hole can also appear too bright by feeding above the gentle limit for brief spells, or by funneling a wind into a beamed cone that points our way. The two pictures compete and the evidence wavers from one to the other, yet a few sources push persistence and brightness to levels that feel more comfortable for an accretor that weighs thousands of suns. Deep in dwarf galaxies, faint nuclei carry narrow emission lines that shift in a way consistent with gas, orbiting a relatively light central engine only tens of thousands to a few hundreds of thousands of suns. These are not the middles by themselves, yet they show that there is no hard wall between the smallest central engines and the larger ones. Black holes live in stripped cores in compact dwarfs in nuclear star clusters, and may grow in steps by eating their neighborhoods. A dwarf that falls into a larger galaxy and is torn apart leaves its nucleus to sink toward the center, with its black hole intact, stepping the mass upward one delivery at a time. A star cluster that undergoes core collapse gathers its heaviest members into the center, through mass segregation colliding and merging until a runaway builds a very massive star that exhausts its fuel quickly and collapses. The resulting black hole, born already heavy, holds the core and can grow by swallowing more stars on errant orbits or by digesting compact remnants that scatter inward. In such a crowded heart, three-body encounters change partners often, and when two black holes pair up, they may merge and hand their kick to the remnant. The recoil can eject it or leave it wandering within the cluster, starting the process again. If enough mergers occur without escape, a stepping ladder builds an intermediate mass. Gravitational wave detectors sense the top rungs of that ladder when two heavy remnants from earlier mergers collide and produce a product that sits in the mass gap carved by the physics of pair instability, where ordinary stellar death should not place a remnant. The catalogues now include a few such events, and while each can be written as a rare stellar evolution pathway together, they favour some hierarchical assembly. The next ears will push toward lower tones where binaries of hundreds to thousands of suns spend long years spiralling and offer advance warning before their final plunge, a band that the space-based interferometer will own. When those tones come, the uncertainty about middles will shrink. Tidal disruptions offer another lighted path. A white dwarf star that wanders too close to a middle-mass black hole can be torn apart outside the horizon, releasing a short hot flare rich in heavy elements, and sometimes showing a bright radio loud afterglow as debris shocks the ambient medium. A stellar mass black hole would swallow the dwarf hole with little show, and a central giant would treat the dwarf like dust. Only the middles have the right size to shred and light. A few events match this description, including bursts with very soft X-ray spectra and rapid rises and falls, long faint echoes in radio light map expanding shells, consistent with a small host environment. Each case is delicate because other astrophysical detonations can mimic the light curve, yet the set of properties aligns best with the middle engine. Even silence holds information. In many globular clusters, the number of tight pulsar pairs and cataclysmic variables is lower than expected if a heavy black hole were present, because a central black hole would harden or disrupt those fragile binaries. Conversely, in a few clusters where binary fractions are high and central density's low room remains for a heavy anchor, the pattern suggests that not every cluster can hold a middle, and that those that do may be special, the densest the youngest in a relative sense, or those that formed with unusually massive stars. The formation paths may require conditions that do not recur often, or they may be brief windows easily missed. Simulations that begin with gas-rich compact clusters born in faint galaxies show that within a few tens of millions of years, a runaway merger can produce a very massive star. If the cluster retains the gas needed to cool, and if the stellar winds are not too strong, the collapse leaves a black hole that already sits in the middle mass range. Such objects then grow slowly by accreting winds and by occasional collisions until an encounter delivers a fresh supply. In dwarf galaxies with shallow gravitational wells, supernova winds may blow gas away before the growth continues, preserving the black hole as a light nucleus that later drifts into a larger galaxy and becomes an off-center wanderer, a fossil marker of a past meal. Observers chase these wanderers through off-nuclear flares and through small compact radio cores that sit away from the photometric center of their hosts. The numbers balance, but the stories do not, because each line of evidence admits rival tales. An ultraluminous source can be a stellar mass black hole with beamed accretion. A cluster velocity cusp can be made by a tangle of orbits and neutron stars. A tidal flare can be a peculiar supernova in a dense environment, and a small active nucleus can be a larger black hole seen through a trick of orientation and obscuration. The way forward is to stack channels until a single identity is forced. A globular cluster that holds a persistent radio core shows a slow central drift in star motions, and hosts a transient that rises and fades with a timescale that fits a few thousands of suns would be very difficult to explain without a middle mass. A dwarf galaxy whose nucleus shows a reverberation lag consistent with a light central engine hosts a radio jet with power appropriate to a few hundreds of thousands of suns, and later sends a pair of low-tone gravitational waves that match an in-spiral at that mass would be decisive. The same logic applies in reverse. If the middle class proves thin or absent, theory must rescue early giants by leaning more heavily on direct collapse on cold streams that avoid fragmentation or on feeding above the gentle limit for long stretches. The terror in the riddle is quiet. Without middles, the universe builds its largest wells with a bold jump, and then hands them empires to rule. With middles, it builds staircases in crowded rooms where collisions and chance encounters decide which rung is occupied. Either picture holds a threat to the simple clock. The former demands speed, the latter conceals power in places we thought were safe from extremes. The likely truth is a combination, a mixture that varies with environment and with time. When the next ears and eyes widen the search, the balance among these paths will sharpen. For now the numbers balance and the stories do not, and that mismatch is the most honest signal available. It says that the middle class is within reach, yet remains elusive, and that to find it one must watch places that have long seemed quiet, with the patience reserved for rooms where sudden decisions are made. A star wanders too close to a black hole and finds itself at the cliff where tides are knives. The pull across its body differs enough between the near side and the far side that the star first stretches, then spills, then breaks into a ribbon of gas that wraps around the well. This is a tidal disruption event, and it offers a rare look at the geometry of feeding, because the pantry is a single star whose fate can be followed from first tear to late ash. Surveys in optical and ultraviolet light catch the first rise as a blue flare that brightens over days to weeks, and space telescopes in X-ray light often find a softer glow that rises more slowly, or in some cases switches on later, as if the inner disk takes time to form. The Neil Gehrels Swift Observatory watches in both bands and can turn quickly when an alert arrives, while ground surveys like the Zwicky Transient Facility and the All-Sky Automated Survey for Supernovae trawl the sky each night and send coordinates to larger telescopes for spectra. The Spectra near-peak show, broad helium and hydrogen, features sometimes narrow lines from gas in the host galaxy that has been ionized by the flare, and a smooth blue continuum like a small hot photosphere radiating from the newly formed debris. In the simplest picture, half the broken star becomes unbound and escapes, while the other half swings onto highly eccentric orbits that gradually lose energy in shocks at pericenter and circularize into a disk. The rate at which debris returns to pericenter sets the feeding rate, and for a while, that rate follows a gentle power law that observers recognize in the fading light. Yet many flares decline differently, a clue that the star was not a uniform sphere, or that winds and reprocessing alter the view. In several well-monitored cases, X-ray emission lags the optical by weeks, a delay that fits a scenario in which a puffed optically thick wind hides the inner engine until the wind thins. Polarization measurements during the bright phase show a few percent of ordered light too small for a bare disk, which suggests scattering by an envelope that smooths out angles. Chandra and the X-ray multi-mirror mission Newton have followed tidal flares into late times and see soft X-ray emission that persists for years, the afterglow of a thin disk that finally touches the innermost stable circular path. In radio, the Carl G. Jansky Very Large Array and other facilities hear a fainter echo as ejecta sweep into surrounding gas and generate synchrotron light. The radio-like curves often turn on late, matching a shock that blossoms after the optical peak has passed, and the speeds implied by the spectra span from gentle to relativistic. In a few dramatic events, the X-ray emission is hard and highly variable from the start, and a bright beamed radio source appears at once, the signature of a jet born with the disruption. Those rare events reveal a link between sudden feeding and jet launch, a link that may require a rapidly spinning black hole and a large magnetic flux already parked near the horizon. Even without a jet, fast winds are common. Ultraviolet spectra with the Hubble Space Telescope show broad absorption troughs from high ionization states that imply outflows at thousands of kilometers per second. As the flare declines, those troughs weaken or shift, mapping the cooling and thinning of the wind. Optical spectra evolve too, sometimes showing helium-dominated features that hint that the victim was a stripped core of a former larger star, sometimes rich hydrogen, that argues for a younger, less processed victim. Each flavor of flare becomes a fingerprint for a different kind of star in a different orbital geometry. Because the star arrives from the galaxy at large, tidal events probe the reservoir of bodies in the nuclear region. The rate at which flares occur depends on how stars diffuse into lost cone orbits that cross the danger zone. In galaxies with compact nuclear star clusters scattering by many small encounters can refill the cone steadily, while in galaxies with triaxial potentials, box orbits wander close to the center more often and feed the well in bursts. Observers compare the measured rate across many galaxies to theoretical expectations and find rough agreement, but with a wide scatter that correlates with central structure. Post-starburst galaxies, which have recently ended intense star formation, show an excess of tidal flares perhaps because they were shaped by a recent merger that left orbits chaotic and sent stars into the center more efficiently. The flare light also acts as a probe of the immediate environment. Narrow lines that switch on and then fade in the host spectrum reveal gas at some distance that is suddenly ionized and then recombines. The delay maps the light travel time, a crude echo that outlines the scale of the nuclear gas reservoir. In dusty nuclei, mid-infrared light rises as grains absorb the flare and re-radiate a dust echo that itself fades on the cooling timescale of the warmed grains. These echoes expose hidden structures without resolving them, a form of tomography powered by disaster. Not every tidal encounter ends in the same way. Around the smallest stellar mass black holes, most stars that come close are swallowed whole with little light. Around the larger central giants, the tidal radius lies inside the horizon, and stars also vanish without a flare, so the sweet spot for bright events lies with black holes of roughly a few 100,000 to a few tens of millions of suns. White dwarf victims add another twist because the tidal radius for a dense degenerate star is so small that only a middle-mass black hole can both disrupt and not swallow. Those events produce very soft X-ray flares and lines that betray heavy elements like oxygen and neon, and they evolve quickly because the debris is compact. A handful of such candidates have been seen, which in turn serve as signposts for the sought-after middle class. A further complexity appears when the black hole is not alone. In a nucleus that holds a pair of black holes, the potential is time-dependent, and stars can be torqued into the lost cone more efficiently. The debris stream itself may be cut by the companion altering the feeding rate, and leaving a light curve with sudden dips and rises that cannot be explained by a single engine. Long monitoring of some flares shows such features, and very late-time spectra in a few cases hint at a small velocity offset in narrow lines that could come from a moving source. No case is decisive alone, but together they suggest that tidal events may offer a quiet channel to find binaries that are otherwise difficult to detect. The most delicate signal lives in how the inner disk appears after circularization. If the disk forms promptly, the X-ray spectrum should harden early, and the light should follow the simple power law decline expected from returning debris. If circularization is delayed because the stream misses itself on first pass and only slowly thickens through relativistic precession and shocks, then the optical peak comes from reprocessing in the stream rather than from a settled disk, and the X-ray turn-on is late and sometimes absent. Observers find both modes, and simulations show that the dividing line depends on black hole mass spin and on the angle of approach. This diversity suggests that the last steps before the event horizon, where gravity turns orbits with precision, can still produce different stories from nearly identical beginnings. The cliff does not dictate a single fate. It dictates a range, and the range is written in light curves that climb and fade with telling slopes. In the most luminous cases, radiation pressure may push back on infall and launch an outflow that traps and thermalizes much of the energy, making a photosphere that inflates and hides the central engine. As the outflow weakens, the photosphere recedes, and the spectrum shifts to higher energies, revealing the disguised core. Polarization should drop as the geometry becomes more axisymmetric, and in a few flares that drop is seen. Finally, when the event has faded to a whisper, a soft X-ray ember remains that can be modelled as a thin disk, feeding at a small fraction of the rate it once enjoyed a quiet end to a violent meal. The debris that escaped becomes a faint stream that wraps the nucleus and may someday fall back as a dribble, while the bound remnant in the centre spins a little faster and weighs a little more. The terror in these events is not the flash itself, but the reminder it carries. A star that lived with steady habits for billions of years can cross an invisible boundary set by a central well, and turn into a short, bright instruction manual for how gravity feeds. The manual is written in light that delays and in lines that skew in echoes from dust, and in radio shells that swell, and its last page is a disk that survives the storm and keeps turning long after the panic has passed. Time near the rim is not a single substance, but a layered weather, a fabric that stretches and drifts depending on how deep one stands in the gravitational well, and how fast one circles the throat. Clocks slow as they descend their ticks, widening like ripples that lose energy and light, that climbs out reddens its crests, pushed farther apart by the climb. The notion is simple in statement and precise in consequence, and instruments have learned to read it by watching clocks made of stars of hot spots, and of quantum transitions in atoms collected by telescopes. In the galactic centre, the Very Large Telescope Interferometer, with its instrument called gravity, measures the orbit of a star that swings within light days of the compact object, and sees not only the speed but the change in the rhythm of its light, a redder tone near closest approach that matches the expected gravitational redshift and special relativistic beaming. The pericenter processes also the ellipse, turning by a small advance each time a slow handwriting of curvature on a canvas of near-classical motion. In the same neighbourhood, the Keck telescopes track sister stars and refine the mass and distance, and together these measures build a local metronome that agrees with the geometry forecast by general relativity, while still leaving a narrow corridor for small deviations that only patience can close. Closer to the edge, timing turns from years to minutes and seconds. Hot spots in the inner flow flicker as they orbit, and their light curves carry quasi-periodic hums that match orbital periods only a few gravitational radii from the rim. When the Event Horizon Telescope teams assembled their ring portraits, they also searched for patterns in brightness that circle the ring on human timescales, and found hints of motion that matches orbits with periods of tens of minutes in the Milky Way case. In higher energy bands, the Neutron Star Interior Composition Explorer watches stellar mass black hole binaries and sees quasi-periodic oscillations at hundreds of cycles per second, small modulations that many models tie to motion in the throat, where frame dragging twists space and nodal planes precess. If matter slightly tilts with respect to the spin axis, the lens-thirring effect rotates that tilt, changing the face the flow presents and modulating the light. The beat is not wholly steady. It drifts and splits as if more than one ring of gas participates, and as if the thickness of the inner flow swells and thins, but through that complexity the core message remains near the rim. Orbits carry a timestamp that can be read in light. Even delays between colors act as rulers. Reverberation mapping in active nuclei measures the time between a burst in hard X-ray light from the corona and the softer echo from the reflecting disk numbers that come in as seconds for stars and tens of seconds for millions of suns, and when scaled by mass they agree with a picture in which the lamp hovers only a few gravitational radii above the mirror. A further and subtler delay comes when light skirts the photon sphere, the last ring of unstable paths where photons can loop partway around before escaping. That loop adds a fraction of a millisecond for stellar mass objects, and minutes for giants, delays too small to isolate cleanly, but large enough to shift interference patterns in a way that can be sensed with long baselines or with very high cadence timing. In the best circumstances, multiple paths produce a primary image and fainter ringed echoes that carry a geometric series of delays. Instruments today can only place limits on such subrings, but the geometry leaves a signature even when blurred, a slight bias in inferred diameters, and a preference in phases that points to the presence of those precarious paths. Time also tilts because space itself is dragged by spin. Around a rotating black hole, inertial frames swirl, and gyroscopes would slowly precess even in the absence of torque. In the language of the accretion flow, tilted disks align their inner regions with the spin, while their outer parts keep the memory of the larger galaxy, and the boundary between aligned and misaligned zones can shift as the feeding rate and the magnetic pressure change. That shifting boundary writes a long-term modulation into jet direction and into the polarization angle of near-horizon light, slow drifts that observers have begun to log over years. If a binary black hole lives in a nucleus, the combined spin and orbital angular momentum carve a more complex pattern, imprinting a slow precession on the inner nozzle that can leave S-shaped distortions in radio jets and a mild wandering in the clock of flares. Against these grand drifts, local clocks still tick. The iron line reverberation from X-ray spectra shows red wings that deepen when the corona sinks, and the lag between continuum and reflection shortens by a heartbeat when the lamp drops by only a few gravitational radii. In that small full time changes enough to rewrite the sequence of glints from different annuli in the disk. The corona itself behaves like a clock with an erratic spring, sometimes compact and close, sometimes extended and faint, and each state establishes a new choreography of delays. The line between steadiness and chaos is crossed most clearly when a quasi-periodic oscillation appears, and then vanishes as if a preferred radius forms and dissolves a transient ring of order at the edge of a storm. At the smallest scales that the instruments can sense in the Milky Way center, near-infrared flares swing their polarization angle in a loop as if a compact blob orbits, and the period inferred is consistent with motion at the innermost stable circular orbit for a moderately spinning black hole. The loop is not perfectly closed, hinting at expansion or at a changing field, and the period drifts by a few minutes between nights as if the hot spot forms at slightly different radii each time. Precision is good enough to corner such changes, but not yet to settle whether the drift is driven by the spin or by turbulence. A magnetar close to the center adds noise and opportunity its pulses delayed and scattered by the plasma that fills the region. Those delays can be turned into a measure of the medium that the flares must cross, which tightens constraints on how much foreground structure can masquerade as changes near the rim. What makes time near the rim terrifying is that it is both rigid and sly. The basic relations between mass spin and orbital period are strict. An orbit at the innermost stable path for a given spin has a fixed frequency, and light, climbing a given gravitational potential, will redshift by a definite amount, And yet what the instruments see when they sample that rigid structure are modulations cast through weather winds that scatter coronas that rise and sink hotspots, that form and dissolve jets that align and precess, and disks that warp and thicken. Each layer adds a local delay or a phase shift that overlays the fundamental beat. Removing those layers is the art that turns observation into a clock, and once removed, the remaining beat can be compared with the forecast. So far within the precision available, the beats agree with the classical score, but the residuals keep a shape. In a few stacked gravitational wavering downs, a faint suggestion of echoes appears at delays that map to distances only a few Planck lengths outside a horizon, if interpreted literally an audacious frame that remains unproven but refuses to go away. In radio images of the ring, slight deviations from circularity at the level of a few percent could be signs of spin combined with viewing angle, or of flows that are not perfectly symmetric, or they could hide a tiny displacement that would betray a non-smooth boundary. In X-ray, lags a persistent preference for slightly shorter delays than expected. In specific sources could be a sign that the lamp sees a warped surface and not a flat mirror. None of these rise above the bar for certainty, but together they hint that the last percent of agreement holds the largest room for change. The path forward is clear in outline and arduous in detail. Longer baselines for radio to resolve subrings higher cadence, and throughput for X-ray timing to catch lags that change in a single flare, and more sensitive gravitational wave ears to separate overtones in the ring down with confidence. With such tools, the clocks near the rim will be read with fewer layers in the way. If the fundamental beat then shifts, the shift cannot be dismissed. If it does not, the constraint will be as terrifying as a discovery, because it will mean that the boundary beyond which time stops speaking remains perfectly mute, even as we listen from only a few gravitational radii away. The classical horizon is drawn as a perfect silence, a one-way edge that lets matter and light cross inward, but forbids any message to return, and that drawing has guided generations because it is simple and because it works. Yet quantum rules insist on bookkeeping for information, and when Hawking radiation is allowed to leak outward from the vicinity of the horizon, a paradox appears. If radiation carries no memory of what fell in, then unitarity, the idea that quantum histories preserve information, would be broken. If information does emerge, then the horizon cannot be perfectly mute. The problem is sharpened by entanglement. Fields near the edge knit their states across the boundary, so that the outgoing quanta are entangled with partners behind the line. Near the end of evaporation, either the entanglement with the interior must be cut, or the new quanta must be entangled with older ones in a way that avoids duplication, a choice that seems to violate one principle or another if the horizon remains a smooth place for an infalling observer. This tangle gave rise to the firewall proposal, a stark claim that the horizon becomes a searing wall of high-energy quanta that breaks the equivalence principle and burns infalling matter at the edge, thus preventing the paradox by destroying the comfortable vacuum there. The proposal is terrifying in its bluntness and attractive in its willingness to pay a price, but it collides with the expectation that low curvature regions should look locally benign, and so many look for a softer compromise. Another path comes from string theory, where detailed counting of microstates for certain supersymmetric black holes suggests that the smooth interior may be a mirage, and that each microstate is instead a horizon-sized complex structure, a fuzzball without a traditional interior. In that picture there is no place for information to vanish, because there is no empty inside to hide it, only a tangled exterior that radiates like a warm surface with a memory. A third approach dresses the horizon with soft hair. very low energy degrees of freedom associated with large gauge symmetries that could carry a record of what has fallen in and alter the outgoing radiation by a small but sufficient amount to encode information. Recent advances in quantum gravity also hint at islands in the bookkeeping of entanglement regions that count as part of the exterior for the purpose of entropy, even though they lie behind a would-be horizon, a calculation that allows the total radiation entropy to bend at the expected time and decline, restoring unitarity without a brutal wall. All of these pictures seek to answer the same question with different costs, and each leaves a boundary where the next question waits. Observers cannot put a probe into the horizon, so they read the edge indirectly by looking for signs that the boundary is not perfectly absorbing. A horizon with even a slight reflectivity would create delayed echoes in gravitational waves after a merger, faint regularly spaced bumps trailing the ring down as radiation bounces between the light ring and the surface and leaks out in steps. Teams have searched stacked catalogues and individual loud events for such echoes, and report hints that hover below firm significance. The absence of decisive echoes constrains how reflective any surface could be, but it does not enforce perfect silence, because the reflection might be frequency dependent or might be swamped by turbulence in the remnant. Imaging offers another doorway. If a surface replaces the horizon, some of the matter that would have fallen through must pile up or radiate after a delay, creating a persistent glow inside the silhouette, or a flickering hotspot that repeats with a pattern set by orbital periods near the edge. The Event Horizon Telescope has not seen a bright interior, and limits on interior emission already rule out simple hard surfaces that re-emit like ordinary matter, but more subtle structures could avoid that constraint by trapping light for long times, or by converting energy into channels we do not image well. Polarization at the ring maps ordered fields that thread the brink, and any persistent coherent shift in angle that refuses to track changes in the flow might betray a boundary effect. Yet current swings can be ascribed to the churning in a disk, and the frontier between flow and edge remains hard to draw. X-ray timing also probes the distance between the lamp and the mirror, and a mirror that moves with the inflow or sits slightly outside the classical radius would change the lags by a small fraction, a change that some sources may hint at, but that none demand. The membrane paradigm gives a classical language for an otherwise unreachable edge, treating the horizon as a stretched surface with electrical resistance, viscosity, and conductivity. That language has proven useful when building models of jets and disks, because it replaces an absence with a set of boundary conditions that conserve energy and charge. If the true quantum edge has additional structure, it may look like a slightly modified membrane, one that can store and release a little more information and reflect a tiny slice of the storm. The danger is to overfit. Any real accretion flow is turbulent and time variable, and small drifts and echoes can arise from changes in the corona, from winds or from the bending of light in a thickened atmosphere. To claim hair or fire or fuzz, one must find a pattern that cannot be made by weather. Gravitational wave ringdowns come closest to such purity because the environment is quiet shortly after a merger, but even there nonlinear couplings among modes and mild asymmetries can mimic late-time structure if not modelled well. Theoretical tools have improved with numerical relativity able to evolve mergers with unequal masses and high spins, and to include more harmonics and overtones in template banks. As these tools refine the room where new echoes could hide shrinks, and any residue that remains will gain weight. On the theory side, the most promising hints that do not ruin ordinary experience come from soft modifications that respect the equivalence principle at accessible curvatures and yet change global entanglement bookkeeping. The island prescription in gravitational path integrals reproduces the correct page curve for evaporating black holes in controlled settings, and does so without creating a violent wall for an infaller, but extending those arguments to realistic asymptotically flat spacetimes remains challenging. Complementarity remains a guiding story, suggesting that no single observer can witness both a smooth horizon and the retrieval of information, and thus no contradiction appears in a single diary, but complementarity must be implemented in a precise theory, not only as a slogan. Fuzzball ideas offer explicit microstate geometries in special cases, but connecting those special cases to the astrophysical giants that telescopes see still requires a vast bridge. Soft hair ideas connect infrared symmetries of gauge theories with conservation laws that could remember what fell in, yet turning that memory into practical decoding of Hawking radiation is a step not yet walked. Through this landscape, the boundary answers with another boundary. Every time the line is approached with a new tool, the tool finds agreement with the classical picture to within a percent and leaves a percent unexplained. That unexplained part is where each proposal tries to live. It is possible that the horizon is as smooth as the classical drawing, and that unitarity is saved by subtle global bookkeeping that no local probe can test. It is possible that the horizon is replaced by a complex exterior that looks smooth at our precision, but will show small departures when baselines are longer and waves are cleaner. It is even possible that the paradox dissolves when gravity is fully quantum, and that our split between inside and outside is not fundamental. For now, the empirical instructions are modest, and strict measure ring-downs with enough precision to separate overtones, cleanly image rings with enough resolution to see sub-rings, and track persistent offsets and map lags with enough cadence to watch a lamp rise and fall by a few gravitational radii. If nothing deviates, the silence itself will grow threatening, because it will imply that information escapes by a path that hides perfectly from instruments that stand only a breath from the brink. If something deviates even by a little, the deviation will be the first word spoken by a boundary that was supposed to have no voice. A black hole is defined by an absence of region from which no light returns, but theorists have long explored whether the absence might be replaced by an exotic presence that performs like a hole without possessing a conventional interior. One proposal dresses the core in a shell where space-time undergoes a phase transition, a graver star with a dark energy-like interior matched to an ultra-stiff crust. Another builds a compact star from a field rather than from fermionic matter, a boson star that resists collapse by the coherence of a light scalar wave. A third imagines a collapse that halts at extreme density and rebounds into a white hole after an immense time as measured from the outside, a Planck star scenario in which the interior acts as a spring compressed by quantum geometry. Wormholes offer yet another substitute passages to a second region that mimic a deep well on one mouth, but without a horizon, if held open by exotic stresses. Each of these cores without centers respects some pieces of known physics, and bends others, and each predicts signatures that differ slightly, sometimes only slightly from the predictions for a true horizon. The most basic signature is the behavior under tides. A black hole in general relativity has zero tidal love numbers, meaning it does not deform in response to a gentle external field. A star or any object with an internal structure does deform, and therefore adds phase shifts to the gravitational waves during inspiral. Current interferometer data can limit such deformations for heavy binaries, and the limits lean toward the strict case, yet the uncertainties are still broad enough to allow thin layers that would deform only at scales smaller than present sensitivity. Tidal heating presents a second test. An absorbing horizon swallows some energy and angular momentum during inspiral, which alters the phase accumulated before merger. A reflecting surface would heat differently. Analyses of several loud events show consistency with absorption at the level expected for horizons, but the error bars leave room for small departures, and those departures are precisely where structural alternatives seek to live. After merger, the spectrum of ringing tones carries a fingerprint of the exterior geometry. A black hole's quasi-normal modes depend only on mass and spin. An object with a surface or a throat would add extra tones or slight shifts in the main ones, and in extreme cases produce late-time echoes caused by waves bouncing between a photon sphere and a reflective boundary. Stacked searches for echoes have produced teasing hints that have not yet cleared the bar for a claim, while careful modelling of higher overtones in ordinary ringdowns tends to favour the classical spectrum. Still, the absence of decisive anomalies is not a defeat for alternatives, because many versions are engineered to make departures only at levels that will become measurable as detectors improve. Electromagnetic clues complement the waves. A true horizon accepts infalling matter without a terminal flash, but a surface would radiate when struck. If the central engine in a galactic nucleus were a star-like object with a very compact surface, steady feeding should produce a persistent glow from that surface atop the variable disk. Limits from the Event Horizon Telescope images and from infrared timing in the Milky Way center already disfavor the simplest hard surfaces that would re-emit efficiently. Yet a graver star shell could swallow and reprocess energy in channels that are dim to our eyes, or a boson star could deflect matter into orbits that never reach a hard boundary, spreading the energy across a thicker, cooler atmosphere. Imaging of photon rings offers another route. The diameter of the ring around a genuine horizon is fixed by mass and distance to within a few percent, while a boson star or a wormhole throat could change the light bending slightly, as could a surface that reflects or refracts in a frequency-dependent way. Present images of the Milky Way and of the Virgo Giant are consistent with classical predictions, but the tolerances are not yet tight enough to exclude finely tuned alternatives, and subrings that would sharpen the test remain unresolved. Lensing also distinguishes among candidates at larger scales. A boson star with a soft density profile bends light differently than a point mass affecting microlensing curves of background stars. Ongoing surveys find mostly point-like behaviour, again placing gentle pressure against a diffuse alternative. Inside galaxies, stellar motions near the centre respond to the precise shape of the potential. The clean Keplerian fall seen in the closest stellar orbits near Sagittarius. A star fits a compact mass with negligible extended component within that radius. Any core with a wider density profile would have left a detectable deviation unless its true extent was smaller than the current observational window. Pulsar timing in close orbits would test the quadrupole moment of the central object, and therefore its multipole structure against the no-hair theorem, but the needed pulsar has not yet been found. Simulations and searches continue because a single detection could turn geometry into numbers. Stability is a further sieve through which many exotic objects must pass. Boson stars can be stable only in narrow ranges of mass and particle properties, and can fragment when spun rapidly. Graver stars must avoid cracking in their shell under small perturbations, and must not radiate away their pressure support. Wormholes require forms of stress that violate energy conditions unless cleverly engineered with modified gravity that has not yet won observational sanction elsewhere. Planck star scenarios must reconcile the apparent longevity and calm of supermassive engines with interior rebounds that eventually must talk to the outside. If the talk is too loud, it would have been heard as bursts that do not appear in the counts. Where instabilities cut down the parameter space, the remaining slivers are arranged to look as much like a black hole as possible in ordinary tests. Difference hides in the last percent. Dark matter can play at being a partner in this masquerade. Spikes of cold, dark matter around central masses would alter the inspiral of compact objects that fall in adding, drag, and changing phases. If a central object were itself a dark compact halo, its response to tides would deviate from the null case. Pulsar timing arrays that now report a low-frequency background, likely from supermassive black hole pairs, could in principle constrain how much extra phase shift is tolerated. The current signal agrees with classical assembly, yet the models have room for small environmental effects. Another fine thread is spun by superradiance. If ultralight bosonic fields exist, a spinning black hole can seed a cloud that grows by stealing spin and radiates monochromatic gravitational waves. Surveys of spins for stellar mass and supermassive black holes already show deserts in which certain combinations of mass and high spin are rare, consistent with the extraction by such clouds. If the central engines were not black holes but objects with surfaces, or with different far-field multipoles, the growth of clouds could stall or accelerate in distinct ways. In that sense, the presence or absence of superradiant deserts become the cross-check on identity. In every observational lane, the classical picture fits first, and alternatives linger at the margins waiting for a mismatch that stays under scrutiny. That waiting can feel like erosion, but it is also a kind of instruction, because it sharpens which features are essential and which are decorative. Essential are the tight ties between mass spin and ring-down frequencies, the near-zero response to tides at leading order, the size of the silhouette, the absence of a durable interior glow, and the specific timing between hard and soft echoes in X-ray light that anchors a compact corona only a few gravitational radii above a reflecting disk. Decorative are many details of weather that can cloak small structural differences. Absence, therefore, performs like presence a horizon that hides all structure can be imitated by a structure that hides behind a near-horizon disguise. The path to a verdict runs through precision. Detect several clean ring downs with separated overtones, and look for tones that do not fit any black hole spectrum. Resolve subrings in images and measure stable offsets and asymmetries that cannot be blamed on flow or on scattering. Time in spirals long enough to weigh tidal deformability in a mass range where stars cannot exist. Watch for sudden flares that repeat with a delay that matches a bounce. If the results keep defaulting to classical values, confidence will thicken that the interior really is not an interior at all, only a region removed from communication. If a small repeatable excess remains, the excess will be the outline of a new kind of center made of absence, and the most terrifying part will be that the universe can wear two faces so well that only the last percent reveals which one is true. Two mysteries rhyme without agreeing. Dark matter sculpts the large-scale map of the universe yet refuses to glow, while black holes sculpt the centers of galaxies and shine only by what falls in. Where they meet, hidden mass and hidden interiors may trade influence, and the traces of that trade begin to appear in the light and in the timing of motion near galactic cores. A central black hole that grows adiabatically inside a halo steepens the dark matter density into a spike, concentrating invisible mass within a few parsecs and raising the chances that whatever dark matter is, it will betray itself. If dark matter particles annihilate when they meet, a spike multiplies interactions and could send gamma rays outward with energies set by the particle mass. The sky holds a soft glow toward the center of the Milky Way that could be explained by pulsars or by complex cosmic ray propagation, yet the shape and brightness have long invited the possibility of annihilation in a cusp. A precise spike would be eroded by the jostling of stars by gravitational scattering from a nuclear cluster and by past bursts from the central engine, so any surviving enhancement would be modest and clumpy, more like a braided fog than a knife. Still, a braided fog is enough to raise the expected flux within a degree of the centre, and instruments continue to compare maps of gamma light with stellar distributions and gas lanes to separate the components. In nearby dwarfs where ordinary backgrounds are quiet, central black holes of intermediate mass, if present, would thicken the annihilation signal by steepening the halo, and long integrations build limits that now constrain the combination of particle mass and cross-section in the simplest models. A converse influence flows the other way. Feedback from accretion and jets heats and stirs gas which can puff up the central mass distribution and reduce the gravitational pull that would otherwise draw dark matter inward, weakening central cusps in halos. Repeated bursts over cosmic time can flatten the inner profile of a dwarf, leaving a core rather than a cusp, while the largest galaxies with sustained jets can maintain hot atmospheres that alter how baryons settle, and thus how dark matter contracts. The two components therefore co-evolve even if they never collide directly. That coevolution extends into the earliest times where candidates for the first seeds of supermassive black holes include peaks in the dark matter field that gather gas more efficiently, and where a halo with a warm or self-interacting dark matter species might suppress small clumps and change the frequency of early direct collapse. If self-interacting dark matter creates cores rather than cusps, the central density remains low and seeds grow more slowly. If the interaction is velocity-dependent, cores appear in dwarfs, but not in giants, changing where middle mass black holes can take hold. Primordial black holes enter as a boulder link proposed as a fraction, or as all of the dark matter. Surveys of micro-lensing the smoothness of the cosmic microwave background, wide binary stability, and strong lensing of fast radio bursts carve away much of the possible mass range, but narrow windows remain. If a non-trivial fraction of dark matter is made of ancient black holes, the seeds for early giants could be present from the start, and their mergers would contribute to the low-frequency gravitational wave background now hinted at by pulsar timing arrays. Yet the same background would rise too high if the fraction is large and the merger rate steep, so the allowed slice must be thin. Black holes also act as nets for particles. Non-annihilating dark matter can be gravitationally focused and captured into bound orbits that pack the inner parsec, changing the precession of stars and adding a slight drag on compact objects that in spiral. Extreme mass ratio in spirals into central black holes, the clean targets of space-based gravitational wave observatories, would then carry phase shifts that betray a dark matter mini-spike. The amount of shift depends on the slope and normalization of the spike, and on whether scattering by the stellar cusp has softened it. Predictions show that even a mild enhancement can leave a measurable drift in the accumulated cycles before plunge. If the orbit spends long periods at radii where dark matter still dominates over gas, opening a route to weigh invisible mass distributions indirectly. In the realm of ultralight fields, a different partnership emerges. A spinning black hole can amplify waves whose phase pattern matches its rotation, a super-radiant process that seeds a cloud of bosons and drains spin. Axion-like particles become candidates that, if their mass lands within a broad window, would build macroscopic clouds around stellar or supermassive black holes that in turn radiate nearly monochromatic gravitational waves. Catalogues of black hole spins show deserts where high spin and certain masses are rare, as if clouds have already swept those patches. If such fields also compose a slice of dark matter, then black holes effectively act as detectors, translating rotation into limits on particle properties. In dense galaxies, dark matter annihilation near the core could produce electrons and positrons that glow via synchrotron radiation in the magnetic field stirred by the accretion flow. The spectrum and size of that glow would track the field strength, and the density profile and high-resolution radio images of the innermost region can be tested against such an addition. Present pictures of the central ring leave little room for a bright annihilation core favouring either weak cross-sections or shallow spikes, but faint extended components remain hard to isolate from turbulent plasma. Outside, photons, neutrinos from annihilation or decay offer a ghostly messenger nearly immune to the chaotic centre, and detectors tally upward crossing events from the direction of the galactic core, placing supplementary limits that rule out the brighter corners of parameter space. A more subtle signal lives in the orbits of stars. If dark matter contributes significantly inside the closest orbits around the Milky Way's giant, the classic precession would include an extra Newtonian retrograde term atop the relativistic advance. Current measurements of the most bound star are consistent with a clean black hole potential, plus a small smooth background. The room left for an additional dark component within the orbit is thin. In galaxy clusters, the combination of strong lensing arcs, weak lensing shear and X-ray pressure maps shows that dark matter holds most of the mass even in cores with active jets. Yet cavities blown by those jets redistribute both gas and dark matter adiabatically. The feedback loop therefore ties visible weather to invisible scaffolding. On smaller scales, dwarf galaxies whose star formation shut down long ago remain excellent laboratories, because the light is minimal and the halo dominates. If a middle mass black hole lives in such a dwarf, stellar motions would show a sharp upturn in the central dispersion, and a spike would raise the annihilation rate. Cross-matching stellar kinematics radio searches for compact jets and deep gamma-ray limits will decide whether such dwarfs hold quiet wells that heighten the dark signal. The possibility that dark matter is partly a field and partly a relic of early collapse keeps the question open on both ends. If a small slice of dark matter is made of primordial black holes, telescopes should see microlensing at a rate that aligns with that slice, and gravitational wave events with masses and spins that reflect early not-stellar origins. If another slice is made of ultralight bosons, black hole spins in the corresponding mass bands should avoid maximal values, and persistent gravitational waves at specific tones should appear with amplitudes set by the cloud density. If the remainder is a weakly interacting particle, spikes near certain nuclei should add to gamma and radio fluxes at levels just under current limits. None of these outcomes has been forced yet, but each is close enough to be worth the long stare. The feeling that both mysteries conspire is strongest at the centre, where black holes collect and organise gas, while dark matter arranges a quiet background that nudges the orbits and sets the potential floor. When their effects are teased apart, they rejoin in models that must embrace both, because neither reaches its present shape alone. The terror here is not theatrical. It is a slow fear that the universe's two most secretive components share techniques feeding in shadows and leaving only indirect imprints. If the next instruments hear phase shifts in spirals that match mini-spikes, if spins avoid deserts that empty at just the boson masses favoured by other hints, if dwarfs with central wells light up just above the canonical annihilation prediction, then the rhyme will stiffen into a rule. If not, the absence will still teach, forcing both unknowns into narrower rooms, where their stories must be sharper to stay unsolved. Sharper instruments gather on the horizon of possibility, and each promises either a decisive clue or a deeper puzzle. The next generation Event Horizon telescope will add dishes, widen frequency coverage, and in partnership with antennas launched into orbit stretch very long baseline interferometry beyond the diameter of Earth. With longer baselines, the ring that frames a shadow will divide into subrings thin-lensed loops stacked by geometry, and the separation among them will carry a clean measure of mass spin and inclination. Small deviations from circularity now hovering at the edge of detectability will resolve into patterns that can be tested against models of magnetized turbulence and against more radical sketches that grant the boundary a reflective mood. Polarization maps will become movies rather than snapshots, tracing how ordered fields near the brink untwist and retie during flares, and the phase of those swings will be cross-checked against X-ray echoes to tie radio and high-energy light into a single choreography. The Nancy Grace Roman Space Telescope will widen the lens in time-sweeping broad fields for micro-lensing by compact objects and hunting for the subtle magnifications that would betray a thin population of primordial black holes. Its infrared surveys will reveal dusty nuclei brightening and fading on short cycles, a sign of compact feeding that optical surveys often miss, and will deliver light curves that sample the intermediate mass range better than today's patchwork. The Vera C. Rubin Observatory Legacy Survey of Space and Time will turn the sky into a nightly theatre, catching tidal disruption flares, nuclear transients, and the first signs of wandering off nuclear engines dragged in by stripped dwarfs. Together, these wide eyes will populate statistics with thousands of events, allowing patterns to emerge that small samples hide preferred host types, clustering in time after galaxy mergers, asymmetric rise and fall, times that signal either delayed circularization or prompt accretion, and rare repeating flares that hint at binaries. The square-kilometre array will listen in radio to faint cores and to relic lobes left by ancient jets, mapping weather in cluster atmospheres through ripples and shocks and placing direct calorimetric limits on how much energy engines dump into their surroundings over tens of millions of years. That constraint will feed back into models that tie jet power to spin and magnetic flux near the horizon. If power scales with spin as strong field theories predict, then the distribution of lobe energies and ages will become a slow readout of how often engines are refueled and how fortune favours magnets in the inner flow. In high-energy light, the Advanced Telescope for High-Energy Astrophysics and the LINX concept designs push toward better spectroscopic resolution and faster timing. Iron lines with red wings will be measured with enough precision to separate contributions from reflection winds and returning radiation bent back by gravity. High-cadence timing will catch reverberation lags as they change during a single flare, revealing a lamp that rises and falls by a few gravitational radii in minutes, and tracing the response of the disk annulus by annulus. Polarimeters that register the direction of X-ray electric fields will add a fresh constraint on corona geometry, distinguishing a narrow spine at the axis from a broad patchy fog, and will track swings that accompany quasi-periodic oscillations to test whether nodal precession truly writes that beat. Gravitational wave astronomy will cross a threshold when the laser interferometer space antenna opens the low-frequency band where massive black hole pairs sing for years before they merge. Early warning of coalescence months ahead will allow a fleet of telescopes to stare at a single nucleus, ready to watch for a flare before, during and after union. The signal in space-time will deliver exquisite mass and spin, and any electromagnetic burst will then be bound to a specific geometry and time. If no light appears, the silence will itself be informative about how often massive pairs live in gas-rich surroundings. On Earth, new interferometers like the Einstein telescope and Cosmic Explorer will push sensitivity to mergers of stellar mass black holes across most of the observable universe. Cleaner ringdowns with more overtones will map the spectrum of tones more completely, reducing the room where extra echoes could hide. If a persistent residue remains after that sharpening, it will be a stronger case for structure near the boundary. If it vanishes, the classical silhouette will gain authority. The combination of space and ground detectors will also catch intermediate mass pairs, the very targets that link dense star clusters to central giants. Extreme mass ratio inspirals in which a compact star slowly spirals into a supermassive black hole will become clocks and seismographs of the central potential, registering tiny drifts from dark matter, mini-spikes, warped disks, or quadrupole moments that deviate from the simple no-hair form. Neutral hydrogen mapping by next-generation low-frequency arrays will chart the progress of reionization with finer detail, constraining how much early black holes contributed through hard photons and X-rays. That budget loops back to the seed problem: too many early engines would overheat the intergalactic medium. By comparing the faint large-scale three-dimensional map of neutral gas with counts of early compact galaxies and quasars from the James Webb Space Telescope and its successors, the allowed fraction of direct collapse births and of rapid super Eddington feeding episodes will tighten. Space very long baseline interferometry will not only sharpen rings, but will trace jet bases closer to launch. A pair of modest radio antennas in high Earth orbit or on the far side of the Moon would lengthen baselines enough to resolve the nozzle and the first recollimation shocks in nearby jets, tying the orientation of the nozzle to the polarization pattern at the ring and to slow swings in the axis that radio monitoring already hints at. If a stable offset between ring center and jet base persists, models that include a gravito-magnetically dragged inner flow will be favored. If the offset wanders in a way that tracks with flares, magnetic flux loading and unloading will take the lead. Another frontier opens with precision astrometry. Microarc-second measurements of star positions by missions that extend the work of Gaia will detect reflex motion of galactic centers if a central black hole shares its core with a second heavy companion. Even a slow wobble over decades would betray a binary at sub-parsec scales that images cannot resolve. That detection would calibrate the rate at which pairs stall and at which they proceed to merge, anchoring the amplitude of the low-frequency gravitational wave background now suggested by pulsar timing arrays. Neutrino astronomy will step from hints toward patterns. Larger volumes of ice and water instrumented with denser photomultiplier arrays will isolate bursts from individual jets that accelerate hadrons, and time-tagged coincidences with gamma-ray flares will map which engines are hadronic factories and which are leptonic lanterns. If a tidal disruption launches a jet, a cluster of neutrinos might follow within days, a cool proof that a sudden meal can rearrange fields fast enough to open a channel for protons. Finally, the theory that interprets these instruments will become more precise and more testable. Numerical relativity will include more realistic plasmas, radiation transport and quantum-motivated boundary conditions, allowing the small percent differences to be predicted rather than only bounded. Machine learning trained not only on simulated movies but on the raw interferometric data will separate weather from geometry more reliably, reducing the risk that turbulence impersonates new physics. With sharper eyes, the gap can widen because precision removes excuses. If images resolve subrings and still find a stable tiny offset that cannot be blamed on flow, a structural change is required. If ringdowns with many overtones refuse to fit any mass and spin something in the boundary must answer, If extreme mass ratio in spirals collect phase shifts that disagree with a pure black hole quadrupole by a repeatable amount, the central object must carry structure beyond mass and spin. And if none of these occur, the silence will harden into law. Either way is terrifying. The instruments do not promise comfort. They promise fewer shadows in which uncertainty can hide. The future therefore feels like a tightening spiral. As baselines grow and ears become more sensitive, the last percent of mismatch will either sharpen into a message or collapse into agreement. Both outcomes deepen the mystery, one by opening a new room, the other by insisting that the room we already know has no door that our tools can find. The end of a black hole is not an end in the ordinary sense. It begins with a paradox shaped into a law. A black hole has a temperature and an entropy, and therefore it radiates. The temperature is low for giants and higher for the smallest holes, yet never warm enough to touch, except in thought. Over unimaginable spans, the radiation carries energy away, and the horizon slowly shrinks the mass, following a long downward slide that speeds up at the last breath. In this Hawking story, the future contains an era when the largest engines are the last warm objects in a cold universe, glowing faintly while everything else has fallen silent. The radiation is nearly featureless, and yet it must somehow carry the record of what went in if unitarity holds. Evaporation is therefore not a simple fade, but a coded conversation conducted over aeons. Long before that, whisper finishes growth by union, builds a different kind of ending that also begins anew. Galaxies collide and merge, and their central black holes sink toward each other through dynamical friction, slingshotting stars and stirring gas along the way. At small separation, hardening stalls unless a fresh supply of scatterers arrives, or a disk tightens the pair, but in most realistic stories the path continues, and gravitational waves take the lead, carrying energy and angular momentum so efficiently that a final plunge is inevitable. The remnant is heavier and spins with the memory of how the pair met. Cosmology on large scales reads this tree of unions as a background hum in space-time, a low tone that pulsar timing arrays have now hinted at, and the hum itself is a record of growth, written not in light, but in gravity. Each union closes a chapter for two histories and opens a new file for a third. The map of mass and spin across time is the table of contents for that file. The first seeds start the index whether they are direct collapses, heavy stellar remnants that feed fast, or primordials from a compressed beginning. Middle mass objects climb the rungs through collisions in clusters and through the sinking of stripped nuclei. The central giants preside over bulges and halos and keep writing as long as fuel arrives. Feedback cycles regulate that supply, swinging between famine and feast. In the later universe, as gas thins and stars age, the centers tend toward a low, steady diet, yet mergers continue as galaxies grow, by accretion and by capture, and every pair that becomes one adds a line to the low-frequency background and changes the spin of the survivor. Spin is a memory of meals and marriages, and it governs how efficiently a hole can light a jet, and how quickly a corona can return scattered light to the disk. A string of prograde feeds spins the engine up. A mix of tilts and counter-rotations slows it down. Even evaporation will prefer to drain faster from the smallest, least massive remnants left after the fireworks, so the demographic at the end of time favours slow spinners that once were mighty and now fade. If ultralight fields exist, super-radiant clouds may have already mined spin from certain mass ranges, leaving deserts where high spin would otherwise dwell. Thus, the inventory of rotations in the present is both a map of the past and a forecast of which engines will age differently when the deep cold arrives. The thermodynamics of horizons deepens the sense that endings are corridors. black hole entropy scales with area and oddity that suggest that the degrees of freedom live on a surface instead of in a volume. The four laws of black hole mechanics mirror the four laws of ordinary thermodynamics, but the temperature and entropy are geometric. When two holes merge, the total area does not shrink, and when a hole feeds the area, grows in a way that acts like an arrow of time. The area theorem therefore functions as a cosmic bookkeeping rule that survives changes of scale. If quantum geometry modifies the last stages of collapse and evaporation, it must do so without breaking this book. Proposals that turn black holes into gravastars, fuzzballs or Planck stars all inherit the ledger and must balance it. Some do so by distributing the degrees of freedom differently, while keeping the surface story intact. Others do so by allowing the area law to hold on average while local patches wrinkle. The universe in which these rules are taught contains another potential ending that begins again, a black hole that tunnels to a white hole and ejects what it once kept after an external time so long that the event looks like a spontaneous burst in a dark age. In such conjectures, the late universe would have rare, sudden flashes whose energies and durations carry a transcript of ancient collapses. None has been decisively identified, yet the absence of a clear counterexample keeps the door ajar. More cautious versions imagine that evaporation gradually releases correlations so that information returns in the pattern of quanta, not in a single shout, and that the page curve derived in controlled systems really does govern astrophysical giants, saving unitarity with no fireworks at all. The living universe complicates every ending. A black hole does not sit alone long enough to evaporate while stars still burn. It encounters companions, swallows, gas throws jets, carves bubbles, and trades momentum with neighbours. Even after star formation slows, long-lived dwarfs and brown stars drift inward and feed the centre as a quiet rain. Rogue planets and dark clouds wander through and vanish. Compact objects sink and merge. The central region remains a market where many small currencies change hands. In that market, extreme mass ratio in spirals act as precise clocks that tick down many thousands of cycles before plunge each cycle adding phase that can be read to weigh the central geometry. Those clocks will eventually map the quadrupole moments of dozens of nearby giants and test the no-hair prediction with a fairness not possible today. If every map agrees with mass and spin alone, the closure is a corridor to a deeper question. If one deviates by a small but persistent amount, the corridor opens into a new room. The largest structure of all is the fate of space-time itself. If expansion accelerates toward a de sitter like future horizons, broaden at the cosmic scale, and local wells sit within a larger horizon that has its own temperature. In that case, black holes radiate within a bath that also radiates, and the relative temperatures decide the direction of a net flow. Giants colder than the background gain mass by absorbing. Only when the background cools below the hole's temperature can evaporation truly begin. In a universe with dark energy that acts like a cosmological constant, the background temperature never vanishes and the approach to evaporation looks different than in an open cooling void. If dark energy evolves, the balance shifts again. These choices in cosmology are therefore choices in how the black hole era proceeds. The most speculative corridors are those in which black holes play midwives to new regions. Some models of inflation seeded by quantum fluctuations allow a collapsing patch to peel off into a new expansion, creating a baby universe behind the horizon that pinches off from the parent. To the outside, the whole persists. To the inside, a new cosmos flowers. In such pictures, mergers in one universe build the starting conditions in another, and the hierarchy of holes becomes a genealogy. Evidence for such branching is not within current reach, and the narrative remains a disciplined fancy, yet it shows how the most terrifying objects can be imagined as cradles rather than tombs. Through all of these endings that begin again, the mood of the evidence remains calm, insistent, and incomplete. Gravity sets strict boundaries on motion near the brink, and instruments have sketched those boundaries with increasing care. Within those boundaries, small residues and rare events whisper that the story may still turn. Evaporation tells of a ledger that must balance over spans too long to witness. Mergers tell of a tree that keeps growing by cutting and grafting. Feedback tells of cities organized by wells that write weather for their skies. The final terror is quiet and patient. The universe might keep every secret while showing everything, and closure might always open a corridor just as the door seems to shut,